Welcome back, AP Statistics. This is the second part of Chapter 16. We're going to be talking about the geometric model. A model that can tell us how long it will take to achieve the first success in a series of Bernoulli trials is a geometric probability model. So just like Thomas Edison said that he found 1,000 ways that won't work, or 10,000 ways that won't work rather, before he found the first way that works, our geometric model says, well, what are the odds that we succeed after this many fails or that many fails? The geometric probability models are specified by one parameter, right? That parameter is P, which is the probability of success. The models are denoted geometric and then probability of success. We also consider Q. Q is the probability of failure, which is the complement of success. So sometimes it's written 1 minus P instead of Q. Since to succeed first on trial X requires X minus 1 prior failures, the probability of succeeding after X trials is not terribly hard to express. In fact, we used this model, and you didn't even know it, in the prior lesson. All right, so there's a lot of details here. P is the probability of success, Q equals 1 minus P is the probability of failure. X is our random variable, and X is going to be the number of trials until the first success occurs. So on trial X, that's little x, we would have our first success. So if we want to find the odds that we succeed on trial X, we need X minus 1 fails followed by a success. The expected value is 1 over P, which is interesting and really cool. The standard deviation is the square root of Q, or 1 minus P, over P squared. Fortunately for us, the geometric probability model is easily accessible on your graphing calculator. In distribution, you can find Geomet PDF. That is the probability density function, that's the PDF part, for a geometric model, which receives 2 arguments. Now, what is an argument? It's an input. Geomet PDF requires the probability of success, P, and X, the number of trials on which you would like to have your first success. We're going to find the probability that for a set of trials in which there's a 70% chance of success, you don't succeed until the 3rd trial. That is, you want to find the probability that X equals 3. Let's go to it. Here we are at the calculator. Let's go to second distribution. And we're going to go all the way down. I'm actually going to go this way. Geomet PDF. We're going to hit enter. We get that P is equal to 0.7. And we would go down to our X value. We want to succeed on the 3rd trial. We hit paste. And bada bing, bada boom, there's our answer. A little north of 6% chance. Let's do a word problem now. Pastini is a global company specializing in comms security. The company monitors over 1 billion internet messages per day and recently reported that 91% of emails are spam. That's nuts. Let's assume that your email is typical, 91% spam. We'll also assume you aren't using a spam filter. So every message gets dumped into your inbox. That is terrible. And because spam comes from many different sources, we'll consider your messages to be independent. Here's the question. Overnight, your inbox collects email, your poor inbox. When you first check your email in the morning, about how many spam emails should you expect to have to wade through and discard before you find a real message? What is the probability that the 4th message in your inbox is the first one that isn't spam? So we have 2 questions. How many spam emails should we expect to have to wade through and discard before you find a real message? And what is the probability that the 4th message in your inbox is the first one that isn't spam? Okay, So here's how we would do this problem. We want to identify a random variable. We're going to let x be the number of emails until the first non-spam. The expectation is going to be 1 divided by 0.09, and that turns out to be about 11 emails. We should expect our 11th email to be the first non-spam. So to answer the question, how many bad emails are we going to have to wade through? Well, that would be 10 emails. So we're going to get 10 bad emails because the 11th email is the first to be non-spam. Now on to that second question. The probability that x equals 4, that the fourth message is the good one, would be 91% cubed, first 3 messages are bad, times 0.09, the fourth message is good, which would be between 6 and 7%. So there are some problems we're going to run into in which you don't just want to find the odds that trial number, 4 or trial number 5 is the first trial that gets you a success. Sometimes you want to find the odds that the first success is within the first couple trials. And that's many computations, and I don't feel like doing a bunch of computations. So luckily, the calculator has a feature called Geomet CDF. C refers to cumulative, which means the calculator says, okay, what are the odds that it takes, 4 or fewer trials or 5 or fewer trials to get the first success. And it would compute the odds that the first trial is successful plus the odds that the second trial is the first success plus the odds that the third trial is the first success, and so on and so forth. So it takes care of all those computations in one fell swoop, which is awesome. That receives 2 arguments, p, the probability of success, and x, the number of trials at max that we would want to get our first success in. So if you want to get your first success within 4 trials, for example, x would be 4. The PDF, Geomet PDF probability density function calculates the probability of succeeding on trial x. The CDF calculates the probability of succeeding at or before trial x. So for example, the PDF could calculate the odds that the 4th trial is the first success, but the CDF calculates the odds that if you let x be 4, the first or the second or the third or the 4th trial could be the first success. So we're going to find the probability that for a set of trials in which there's a 70% chance of success, we first succeed on one of the first 3 trials. Rather, p of x being less than or equal to 3. So now we're going to go to second distribution all the way to the bottom, Geomet CDF. Our odds of success would be 0.7. The x value is going to be 3. And we hit paste. So we're going to find the odds that within the first 3 we get our first success, and those odds would be very likely, north of 97%. So here's another fun word problem. People with O negative blood are called universal donors because O negative blood can be given to anyone else, regardless of the recipient's blood type. Only about 6% of people have O negative blood. We have 2 questions here. 1. If donors line up at random for a blood drive, how many do you expect to examine before you find someone who has O negative blood? All right, so there's another expectation problem. Number 2, what's the probability that the first O negative donor found is one of the first 4 people in line? Okay, so here's how we'd answer those 2 questions. We're going to let x be the number of donors before one has O negative blood. That's going to be our random variable. The expected value is going to be 1 divided by 0.06, which is 17 donors. We should expect our 17th donor to be the first one with O negative blood. So if the 17th is our first success, How many do I expect to examine before I find someone who has O negative blood? Well, the first 16 are not going to have O negative blood. We expect the 17th will, all right? So what's the probability that the first O negative blood donor is found in one of the first 4 people? 4 is far from 17, but the odds are actually pretty decent. The probability X is less than or equal to 4 is Geomet CDF, and we would substitute 0.06 and 4. This would be our value for P. This would be our value for X. So this would be the odds that the first, second, third, or fourth is our first to have O negative blood. And that, interestingly, has about 21.93% chance.